All right, well, it's 7:04. It looks like we have a handful of people who have joined. Thank you for joining us. This is the Resilient Together Collins Cove Park Neighborhood public presentation. And I think we'll get started with the meeting. We have a lot to get through. My name is Neil Duffy. I'm the Director of Sustainability and Resiliency for the City of Salem. And this project is one that's funded through a grant, a coastal resilience grant, provided by the Office of Coastal Zone Management with the state. And why don't we go to the next slide quickly? Now onto the meeting agenda. We'll do welcome and introductions, which we're doing now. I'll provide a little bit of a background and the purpose of this workshop. Then we're going the main portion of this workshop is to provide project updates, and the purpose is to try to get feedback from community members. We've been working for over a year and a half on some potential flood mitigation alternatives, and really looking forward to the opportunity to share some of these concepts that have been developed and hearing what members of the community think about some of these potential mitigation solutions. Then we'll talk about next steps and take some questions. Next slide, please. So the team, as I mentioned before, this is a project that is funded by Massachusetts Coastal Zone Management Grant. The team consists of myself and Christian team from the City of Salem Sustainability and Resiliency Department, Barbara Warren from Barbara Warren Environmental Consulting, as well as Allison Fry from Salem Sound Coastwatch, have been project members both in concept development and also in outreach and engagement. And then we have the team of engineers from AECOM. Ellen Douglas is the project manager, and Tyler Brinson and Matt Dope are the two engineers that have been working on the coastal and stormwater flooding solutions. And you'll be hearing a lot from them in the coming slides. Next slide, please. So we're going to be providing engagement through something called Mentimeter. I'm not sure if people who are attending have used Mentimeter before, but it's pretty simple. If you scan this QR code with your phone, or if you'd rather open a new browser window, you can do that and go to menti.com, menti.com, and enter the code that you see on the screen. And once you enter that code, then you will be in the interactive window for the questions that we'll be asking throughout the presentation. Alternatively, in the webinar format through city meetings, we don't have a chat window, but we do use the Q&A function. So if you do have questions that you want to ask that are outside of what we're asking in Menti, or have any other issues, then you can do so through the Q&A. And to my fellow panelists, if we see questions that are happening that you are confident of the answer, we can answer those live throughout, and maybe at the end we can review any questions that were answered and see if there are more. So that's essentially how we will manage the feedback, is through Menti and through the Q&A function. Certainly let us know in the Q&A function if you're having issues with those. Hopefully you've had time to set that up as I've been talking about that. And why don't we move to the next slide? So the project area that we're talking about, there are two circles here, two areas that are pointed out on this map. The red area is an area that was the focus of a project that was funded by Municipal Vulnerability Preparedness Grant also through the state 3 years ago, also partnering with AECOM and Salem Sound Coastwatch to study the flooding issues in the Collins Cove and Willows area. And that was a more high level study. about the different areas in this larger area circled in red, and areas to prioritize, and also potential solutions generally. I mentioned there were areas, priority areas that were indicated in that study, and one of those priority areas was the Collins Cove Park neighborhood. And so, in this grant, we've been exploring potential options to address the stormwater, significant stormwater and coastal flooding that occurs in that area, and will continue to increase over the coming years with sea level rise and the impacts of climate change. Next slide, please. So our first Menti question is, do you live in that project area in the Collins Cove Park neighborhood? We'd like to understand, of the attendees who are here, who actually lives in the neighborhood. Okay, looks like we've got, and you can see on the Menti that the login information is on the slide. So if you haven't logged in and have a chance to now, if you don't feel like responding, that's also okay. That's great. That's a decent sample size. Doesn't look like we're getting much more, so we can move on. Hopefully other people can participate in some of the other questions we ask. And now I'll pass it over to Matt to talk about the issues and solutions.
Yeah. Thanks, Neil. So I'm Matt Delp, and I'm serving as a coastal engineer for the project. And I'll be walking you through some of the coastal flooding conceptual alternatives that we looked at as part of this project. But before I get into that, I just wanted to clarify that we'll be looking at, or like, what the different types of flooding that we looked at as part of the study. Neil talked about both coastal flooding, which we're defining as flooding that happens when ocean waters flow onto normally dry land. And then my coworker, Tyler Brinson, will be talking during the second part of the presentation about stormwater flooding, which comes from heavy rains that overwhelm drainage infrastructure and collect or pond on the ground. Next slide. Next slide. So before I talk about some of the conceptual alternatives, I just wanted to talk about some of the flooding that is happening, that's happened historically. Pictured here are some images from flooding that during a storm in December of 2022, in which the park saw flooding in different places. In the upper left, on the left-hand side of the screen, you can see where water started to flood over top of the wall. And then also in the lower left, how it came up through the backside of the wall and flooded behind it. In the lower right-hand corner, the end of Connors Road was overtopped, and water started to wash out into the streets. So this is just examples of some of the flooding that's happening today during major storms. Next slide. And so we looked at some available coastal modeling information from the Massachusetts Coastal Flood Risk Model. And on the left-hand side of the screen, we use that information to map out the extents and flooding depths for a present-day major storm. And the extents and depths from that flooding was pretty consistent with the flooding that the neighborhood has observed during recent major storm events. On the right-hand side of the screen is a future flooding scenario in 2070 with around 4 feet of sea level rise included. And so you can see that there's much wider spread flooding and deeper flooding in those future conditions. Next slide. And so to try to come up, before we came up with solutions to try to protect against that kind of flooding that I was showing in the previous slides, we needed to evaluate the existing shoreline protection structures, of which there are 8 different types of structures in the study area along in the Collins Cove Park neighborhood. Those 8 sections are called out and labeled in the map on the bottom of the slide, with some of the structures being public in green, and the blue structures labeled in blue being private. We had some structural engineers from our team go out and evaluate the existing condition of these structures, and they found, in particular, structures 4, 5, and 7 were either in need of repair soon or were already starting to fail, as section 5 is shown pictured to the right, where some of those granite blocks have started to fall from the seawall. And above that, you can see where the city has put in some temporary flood protection measures during the fall, winter, and early spring months to try to temporarily protect against floodwaters from overtopping that wall. Next slide. So we started to look at, so to try to come up with some solutions to mitigate for that flooding, we looked at, what are some of the available options for flood barriers that could be implemented in the park to protect against some of those flooding events. I'll talk about each one of these options in detail, but I'll just run through them quickly. The 4 that we looked at are a grass berm, a pile supported wall, and a sheeting supported wall, and then an option where we would replace the existing seawall with a new seawall. Next slide. And before I get into each of them in a little more detail, I just wanted to say we also considered some different alignments or positions for these flood barriers. On the left, what we're calling the road alignment is an option where the barrier follows just inside of the sidewalk, and you can see it, an example rendering of what that might look like below in the bottom left-hand corner. On the right-hand side, alternatively, we have an alignment that follows where the flood barrier would follow just landward of the existing seawall. And again, that's an example of that's pictured as a rendering in the bottom right-hand corner of the screen. And next slide. Yeah, and so we'd like to get your feedback, and I think Neil will talk through that with you.
Yeah, I mean, I know Matt just introduced this concept, but if people are having any initial reactions to those 2 different alignments, whether a flood wall is along the shoreline behind the existing seawall, or if there were a flood wall along the sidewalk side or road side of the park. You may not have a preference at this point, given that you just heard this concept, but we'd love to know your initial thoughts. I see a question which I'll answer live. Yes, both of these flood walls, in terms of the flooding, the coastal flooding, would be equally effective, would be built to the same elevation to prevent the coastal flooding in the same way. The road alignment would, you would be experiencing flooding in the park with the road alignment on that side of the wall, on the park side of the wall.
Yeah, and I'll also mention that as part of the design, these wall sections will access points and openings will be designed or included along the alignments in similar locations to where access points to the shoreline or the park exist now, and they would likely be included. They would likely include some sort of deployable or temporary flood protection structure that would only be set up prior to a storm event. But some of those details would be evaluated at a later design phase.
Great. Okay, I think we can move on. Thank you for those responses.
Yeah, so I'll start to talk in the next couple slides. I'll talk about some of the different um, options in a little bit more detail. So the first one is the grass berm, which is essentially a grass-covered mound that acts as a flood barrier, and it would be covered with long, kind of like dune grasses um, to help stabilize the feature. This option would be less expensive than the other ones, has a more natural look, and can also be raised a little more easily in the future if necessary. Some of the cons with it are that it does take up a little bit more, or it takes up more footprint or space in the park and would require regular maintenance. In the upper right-hand corner of the screen is a cross section just to give a little sense of scale of the structure relative um, to some um, flood elevations. And I just want to note that those elevations are referenced to NAVD 88, which is just a, a an elevation reference datum, kind of similar to um, like uh, it's different than mean low water, but the datum is similar in that sense. Zero NAVD 88 is similar to zero mean sea level, just to make a comparison. In the lower right-hand corner of the screen is an example rendering of what the berm might look like for a sense of scale in the park. Next slide.
So we'd love to, through Menti, this is an open-ended question, but just if you have some general thoughts on the berm, that things that you like or do not like, or concerns you may have about that berm option that Matt described, in a few words, like if you're worried about maintenance, or if you like the idea for pollinators, or those types of thoughts would be helpful for us to hear. This is great. Be easy to adjust. Raise, good one.
Mhm. Come on.
And so, yeah, and raising it, one thing that we would need to be trying to figure out is, the width and the footprint of that, so that we can build up on it if we wanted to try to do that. Um, like that it's more natural.
Yeah,
Um,
one thing I'm seeing with the walking path and benches on the berm being nice, that's a good point. There during later design phases, we'll be able to, potentially incorporate amenities and aesthetical features for this option, but also, they can be worked into other options as well. But certainly the berm potentially has some more flexibility in terms of how we can incorporate design features.
this is good. Oh, good. A good concern. City's not always good at maintaining things. Okay, that's a good comment. Definitely something that we've discussed as a project team. Um, but these are all great comments, and feel free to comment in the Q&A also, if you're not on Menti, even if it's not a question.
Yeah, and I'll just touch on one last comment real quick is in regards to the mitigation potential. Um, I'll talk a little bit about the maintenance, additional maintenance for the berm, but for the most part, it has the same flood protection potential in that it would be designed to the same elevation, kind of like what Neil talked about before. However, there might be some additional upkeep and maintenance concerns that would need to be taken into account. All right, so the next option would be a pile supported flood wall. Um, and this would just be a flood wall, um, with some sort of like metal or wood slats that are held up by piles driven into the ground. Um, the exposed portion of the wall would likely be capped entirely in concrete, so that's the only part of the wall that would be visible. Um, it would be approximately 1 to 2 feet wide, but that would be established during the design phase. Um, some of the pros of this option is that it would have a much narrower footprint and take up less space than the berm would. However, con is it would be a slightly higher cost than the berm, and also require some more specialized equipment for um, uh, installing those piles. So again, we have a cross section in the upper right-hand corner relative to some storm elevations, and then a rendering in the lower right-hand corner. And one thing I'll note about the rendering is you can see how kind of right between the people in the middle, there's um, an opening in the wall. That's an example of a location where we could consider some sort of uh, deployable temporary flood protection measure that could be set up prior to a storm event, but otherwise would remain open to make sure that access is maintained and accessible to the beach. Okay, next slide. So I won't talk too much about this sheeting supported wall option. Essentially, it looks the same above it would look almost identical to the pile supported wall option. It would be designed to the same height. The difference is that instead of um, having piles driven into the ground, it would be like a sheeting panel pile that would be form a continuous vertical barrier and driven into the ground. Um, it would still have a similar narrow footprint similar to the last option, um, but would have even less longer term maintenance. Some cons are that it would cost even more than the other two options I mentioned before, and would also require some specialized equipment to install that sheeting. Next slide. And the last option I'll talk about is an option to remove the existing seawall and replace it with a new seawall, likely consisting of granite blocks. Um, this option um, has the greatest longevity and would require the least amount of maintenance to extend its life. Um, However, some of the cons include a higher construction cost and more intensive permitting involved um, with getting it uh, yeah with getting it through the regulatory process. Again, we have the cross section in the upper right hand corner, and then a rendering in the lower right hand corner of the screen. Next slide.
Yeah, so you probably know what's coming with this question. Similarly, we'd love to know, I mean, the walls options aesthetically all look very similar. So we'd like to know how people feel about those options. sort of as a grouping. If there are aspects of the wall options that you like or concerns that you may have about those wall options, we'd love to hear what those may be. Again, whether it's maintenance concerns, cost, the way it may look, longevity, that's a good one. How long will it last? And as Matt said, a little bit later, um, we're going to do some comparisons on these different options to talk through um, how they compare to one another. A lot of engineering and maintenance, not particularly attractive. Okay, good to know. And again, I think the renderings you're seeing are conceptual in nature. So any concept that would move forward would go through a much more significant design process with more feedback. And so we are what we're showing you now is a pretty basic boilerplate example of what something might look like. But that's good to know that sounds like there may be a preference for a berm. Of course, on the Connors Road end, uh, you'd have a wall there no matter what once you get outside of the park. This person likes less maintenance and replacing old walls than using metal or composite. Okay, yeah, I saw a comment on the Q&A too about fiberglass. I don't know, Matt, if there's anything you wanted to mention about that in terms of.
Yeah, I mean that's a good point. We'll be involving the community during later phases of the design, and if that sheeting option were to move forward, we could prioritize the use of um, well, we could prioritize the use of like granite block, but for if for certain reasons we did have to go with a sheeting supported wall, we could avoid using fiberglass as a material and could use steel, or steel, for example, would be an option other than fiberglass.
This is great feedback. We're going to continue. If people have more feedback, just continue to put that in the Q&A.
All right. Yeah, and so now I know I talked through some of the different considerations for each of the options, but I just want to go through those and then describe each of those considerations, and then we'll summarize them all into a table and talk about that. So the first consideration is permitting and regulatory complexities, which is just the level of effort, review, coordination, and approval required from local, state, and federal agencies. Design footprint is just the amount of physical space the alternative occupies on the site. Feasibility and constructability is the practicability of building that alternative given site constraints. Construction cost is, as you'd expect, it's just the costs of construction to build that project and everything involved in that. Maintenance costs are the costs involved with the ongoing inspection, repair, and upkeep required to maintain the functionality of that option over its service life. Next slide. So of the four options, the berm had the lowest permitting and regulatory complexities, where the wall had the highest, just due to the construction below the high tide line. Next. From a design footprint standpoint, the berm took up the most space, whereas the new seawall took up the least amount of space from the existing park. Next one. From a constructability standpoint, the first three options all have kind of the same level of challenges, but we felt like designing a new wall would have the most, just due to, again, the construction in the tidal zone below the high tide line. Next one. From a construction cost standpoint, both the berm and the pile wall were significantly lower than the other options. The putting in the new wall had the highest costs associated with it. And then next one. Alternatively, though, the berm had the highest maintenance costs just due to some of the annual upkeep that would be involved, as well as potentially bringing in new soil and restoring it following larger storm events. Whereas the sheeting wall and the new wall had the lowest maintenance and upkeep costs. Next slide.
Okay, yeah, so we'd love to know your initial reactions. We've gotten them on the different alternatives, but if you're feeling a preference for either the berm option or a wall option, it'd be great to know. If you don't have a preference at this point, that is completely understandable as well. As we mentioned, we'd expect all of these options to be equally as effective. And also, I'll just mention while we're giving you some time to respond, you may have noticed in the renderings on the Connors Road side there was an opening in the wall, and that's because we did receive some feedback and engagement about access to the beach being important. So we wanted to acknowledge that in the rendering, and there would be some sort of deployable gate essentially that DPS would need to install in that opening when we know that there'd be storm events or any other coastal events happening. But we heard from the community in the earlier engagement that access is important. I think we will maybe leave it at that and move on, and again continue. Before we move to stormwater, I do want to just ask maybe the AECOM team or others. There's just one question about how these options would affect the opposite shoreline and the rest of the cove, especially with coastal flooding and waves. I don't know if you want to just respond to that, Matt, or anyone else.
Sorry, I was muted. I can at least speak to, just in general, hardened structures are more, depending on how they're designed, they're more likely to reflect energy or, just deflect it, erosion potentially, further down the beach or in a different part of the cove in this particular situation. So, some of those details in terms of minimizing any, impacts to other parts of the cove would be looked at as part of the design process. But yeah, that being said, in general, like a vertical wall would deflect or do less to dissipate that energy as compared to a revetment or a beach or a cobble berm, for example, or some other types of coastal features that are more effective at dissipating energy. Hopefully that answered it okay.
All right.
All right, with that, I'll pass things off to Tyler.
Thank you, Matt. Hi, everyone. My name is Tyler Brinson, and I'm the stormwater engineer working on this project. Before we jump in to stormwater flood mitigation alternatives, I want to talk about what causes stormwater flooding in the study area. So this study area is susceptible to high intensity rainfall events. Think of a summer thunderstorm that occurs where high intensity rainfall, a lot of rain falls in a very short amount of time. And you can see on the right-hand side of your screen, some stormwater ponding is likely to occur when you get high intensity rainfall. That stormwater flooding that we see on the right-hand side of the screen can be caused by a few different reasons. The first of which is not enough catch basins installed. So as stormwater runs over the street, there aren't enough ways for it to enter into the stormwater system, so it ponds on the street. The second way stormwater flooding is able to occur in the system or in the study area is undersized stormwater pipes. So even if stormwater is able to get into a catch basin, it isn't able to flow through the pipes if they're too small to handle the rate of runoff caused by the storm event. The third way stormwater flooding occurs in the study area is pretty unique to coastal communities. And this is when rainfall occurs at high tide. When this happens, stormwater runoff is unable to flow through the stormwater system and get to Collins Cove as easily as it is at low tide because the stormwater has to push against high tide. Next slide, please. So now we want to hear from you. Have you experienced stormwater flooding in the study area?
Oh, hold on. There we go. Okay, that's great. And again, if you didn't respond, you can respond in the Q&A, but we can move on. I think there may be another question.
And the next question here is, if you have experienced stormwater flooding, where have you experienced it? In the roadway, basement, field, in your backyard? We want to hear from you. So we have some roadway answers here.
Yeah, that's good. And if people have experienced it on their own property or in their basements, that'd be good for us to know as well. We did hear from some people in the first year of engagement that there have been some recent storms where that's occurred. It looks like most of the folks on this meeting have experienced it in the road. That's great. Yeah. December 22nd storm. Great. Not great that you had the flooding, but great comment. Thank you for sharing that.
Okay. We ready to progress through here? So thank you for sharing your experiences. It's always great to hear from you, even when it's about a topic such as stormwater flooding, which we don't want anyone to have to experience. However, to reproduce these experiences that you've had, we were able to create a hydrologic and hydraulic modeling tool, which is shown on the right-hand side of your screen. Throughout the rest of the presentation, I'm going to be referring to this tool as the H&H, which just stands for hydrologic and hydraulic. On the right-hand side, you can see that the modeled stormwater pipes show up in yellow The stormwater manholes and catch basins are the circles in blue. And then on the very right-hand side of your screen, right in the middle, is a red triangle, and that represents a stormwater outfall. So where stormwater goes from the pipes into Collins Cove. The H&H model is a very useful tool that allows us to represent the stormwater collection system, which is everything from catch basins and pipes and manholes and basically every piece of a stormwater system. We can represent it in the H&H model. Not only does it represent the system, but it allows us to simulate rainfall, so different types of rainfall, different intensities, different overall storm depths for different tidal downstream conditions. So we can see the impact that a storm has if it occurs at low tide or high tide. Like I talked about on a previous slide, stormwater flooding can be very dependent on what the tide is doing downstream. The model allows us to visually represent the extent and the depth and also the duration of stormwater flooding here. So where does it flood? How deep does it flood? And for how long? Not only does it show us where it floods, it allows us to see why it floods. So it will show us restrictions in the stormwater system. And then we can see where those restrictions are and simulate, if we remove them, how much flooding goes away and what do we have to do to significantly reduce flooding in the study area.
Hey,
Next
Tyler,
slide.
there's a question
Yep.
about the red lines. I think it's these dashed lines that are.
Sure. Yep. Good question. So those red lines and those kind of see-through shapes are called model subcatchments. They represent the area tributary to catch basins. So if a drop of rain falls in the study area, those shapes have certain characteristics like slope, percentage of impervious area that represent stormwater flowing over the street before it gets into the stormwater system. So that red dashed line is basically just showing where stormwater from that area is directed into the stormwater system. I hope that answers your question. Next slide, please. So now that we've described what the H&H model is and what it's able to do, we're going to show you. On this slide, we're showing inside of our study area boundary, which is that yellow outline, model predicted flooding for a 2070. So we're projecting into the future here, a 2070 intense rainfall event that occurs at high tide. We did a lot of runs here. There were a lot of different rainfalls, a lot of different climate change scenarios and different tides that we considered, but we're only going to show you a handful of them here. So under this condition, the H&H model predicts that there's about 7.7 acres of flooding that would occur in the study area. And while flooding is predicted to occur throughout the study area, it's mainly focused in the area of Collins and East Collins Street from Barton up to the north through Connors Road. Next slide, please. So as I had said, the H&H model allows us to look at flooding under different tidal boundary conditions. So this is model predicted flooding for that exact same rainfall event, the same 2070 thunderstorm, but this time it occurs at low tide. So we can see how the H&H model is able to pick up that subtlety here of how sensitive stormwater flooding in the study area is to just the different tide downstream, how easily water is able to get into Collins Cove. As we saw during high tide, the model predicted flooding was about 7.7 acres. Occurring at low tide, it's about 3.3 acres. So we can see that difference here. Next slide, please. So now that we understand where it floods and why it floods, it's time to look in our stormwater flooding toolkit and see what can we do to help mitigate some of that stormwater flooding. Our toolbox is split up into two different groups. On the left-hand side, we have tools that the city can consider. These are more larger infrastructure construction type projects here. While on the right-hand side, we have tools that the city and residents can consider. A lot of these on the right-hand side are what's considered source control. Basically, capture the rain where it falls and don't allow it to get into the stormwater system. So these types of stormwater flooding mitigation, I'll call them technologies, include things like bio-retention basins and permeable surfaces. Both of these have already been implemented in Salem, in particular, in the Willows neighborhood. Next slide, please. When we look at evaluating stormwater flooding in coastal communities, there's really a three-step process that we follow. I'm going to take you through each of those, but step one includes and focuses on increasing the capacity of the stormwater system. So things like increasing the size of pipes, allowing more flow to get towards Collins Cove, and then installing backflow prevention. So during high tide, we don't have stormwater backing up our stormwater outfalls and flooding the streets. Next slide, please. Before we jump into step one, I want to make sure everyone has an understanding of how the existing stormwater system works. So on the right-hand side of your screen, the yellow pipes represent stormwater pipes. As you can see, flow kind of moves from left to right on the screen, which is shown by the flow arrows here in light blue. Most of the flow from this study area moves towards one stormwater outfall in Collins Cove. You can see it called out on the right-hand side of your screen. What we've seen based on firsthand experiences and our model predictions is that high intensity rainfall can overwhelm this stormwater system in the one stormwater outfall. On the next slide, you're going to see the image on the right-hand side of your screen change. So this is step one, which is size the stormwater system to carry stormwater runoff from that 2070 high intensity storm event occurring at low tide. The image on the right-hand side of your screen, as I said, went through a pretty significant change from the previous slide. All the pipes shown in light blue now are pipes that we've identified as being undersized. So these would be, increasing the pipe size or adjusting the pipe slope to convey more flow through the system towards the Collins Cove stormwater outfall. The two pink squares that you can see on either side of Connors Road along Collins and East Collins Street are two new proposed catch basins. This allows stormwater runoff to more easily get into the stormwater system. The two orange pipes that you see in the lower middle portion of your screen are new pipes. Now, these two pipes create a redundant flow path. A redundant flow path is really good for a few things, but what its main purpose is to allow stormwater another path to get to Collins Cove before it floods the street. So now, if the Collins Cove stormwater outfall on the right-hand side of your screen becomes overwhelmed, there's another path for stormwater to get to Collins Cove before it ponds on the street. Next slide, please. This is that alternative in action. So on the right-hand side of your screen is showing model predicted flooding for that 2070 intense rainfall at low tide. For our baseline here, we had about 3.3 acres of model predicted flooding for this storm event. With all of our stormwater improvements, the model now predicts about 0.2 acres. That's a 94% reduction in the overall flooded acres for this storm event. We also see a reduction in the maximum flood depth. The max flood depth is now about 6 inches to a foot, and it's really closer to that 6 inches range. And we see a reduction in overall flooding of about a half an hour. So that concludes step one of how we tackle stormwater flooding in a coastal community. Up next, we're going to show you step 2. Step 2 is to keep all those same stormwater improvements in there, but this time run it for the 2070. And when I say run it, I mean run the H&H model for that same 2070 intense rainfall event, this time occurring at high tide. So you can see there's still a decent amount of flooding predicted when that intense rainfall occurs at high tide. However, we do see improvements from our baseline scenario. We see a 20% reduction in the flooded area, which is mainly seen in those orange circled areas. Unfortunately, we don't really see a decrease in the maximum flood depth, but a key here is we do see a reduction in the duration of flooding. So when it does flood, if you get an intense rainfall event that occurs perfectly at high tide, we're able to get that stormwater out of here much faster than we're able to now, by about 2 whole hours. Next slide, please. Now it's time for step 3, which is evaluate alternatives for the remaining stormwater flooding occurring at high tide. Now, for this step, we have to reach pretty deep into our stormwater flooding toolkit here and pull out 2 big pieces of infrastructure, that being stormwater pump stations and stormwater storage. Now, it's important to note that we're not looking at these on their own. When we evaluate stormwater pump stations and stormwater storage, we're keeping what we just talked about in step 1, all those stormwater pipe improvements and the backflow prevention, those are included. Now we're supplementing that alternative with a pump station or storage, which we're going to talk about on the next few slides. I know there's a lot on this slide, so I just want to walk everyone through it. We're going to start with the stormwater pump station. With the image on the right-hand side of your screen, the yellow pipe coming from the upper left-hand side, working its way right towards that red triangle, which again represents the stormwater outfall. We know that during high tide and it rains, stormwater has a hard time making its way through the outfall. So what this stormwater pump station allows us to do is, when that happens, stormwater can move to the south through the orange pipe into our circular pump station. This pump station would be approximately 25 feet in diameter and 14 feet deep. There would be 2 pretty large pumps in there that would convey or pump stormwater to Collins Cove during high tide. This stormwater pump station would have a maximum flow rate of approximately 44,450 gallons per minute. Now, I know that's a little hard to conceptualize. It's a really big flow. So in an attempt to kind of conceptualize it for you, your kitchen sink flows at about 3 gallons per minute. So we have a lot of kitchen sinks here that we need in order to convey that flow into Collins Cove when it floods during high tide. This pump station would take about 2 years to construct, with a estimated cost of $3 to $5 million. Now, this pump station has some pros and cons. The pros are that during high tide, it reduces stormwater flooding that we saw on a previous slide. And it has a smaller footprint compared to storage, which we're going to talk about on the next slide. But some of the cons are that it doesn't completely eliminate stormwater flooding during this storm scenario. There's still about an acre of flooding predicted upstream. It's a large piece of infrastructure, which has some pretty serious constructability and operation concerns. Anytime you're constructing a large piece of infrastructure in a public park this close to the cove, it leads to constructability concerns. The pump station also has the potential for infrequent use. Again, it would only really be needed when an intense rain event occurred at high tide. So there is that potential for infrequent use. And then there's also above grade permanent features. There would need to be an electrical box and then access hatches that are large enough to remove the pumps if they need to be serviced. So that would be a pretty decently sized access hatch. Next slide, please. Now we're going to talk about stormwater storage. Now, I don't want to scare anyone. On the image on the right-hand side of your screen, this is just a conceptual representation. So these, any sort of storage tank that could be constructed here does not necessarily need to be a perfect square, and it doesn't need to be sited exactly in the middle of the baseball diamond. We can play around with the size and the shape. But this is just here to give you a sense of scale for how big this piece of infrastructure would need to be in order to have a meaningful impact on stormwater flooding occurring at high tide. So in the image, we can see our stormwater system. Again, it's those yellow pipes. And then we see an equalization chamber here, right in the middle of East Collins Street. All this would be subsurface. But what this equalization chamber allows us to do is efficiently divert stormwater to any storage tank that would be in the park. Once at the storage tank, we see a range of sizes here, ranging from the kind of smaller dark blue square, which is about 500,000 gallons, to the biggest kind of purple square of 2.5 million gallons. A piece of infrastructure this big would take about 3 years to construct, and it would have a construction cost ranging from $30 to $50 million. And that range is really just due to the difference in size here. Some of the pros are that we meaningfully reduce stormwater flooding during high tide when you look at your larger tank sizes. And it can be used during larger storm events that occur at low tide even. However, this is an even bigger piece of infrastructure than the pump station that we just talked about, leading to, unfortunately, even more severe constructability concerns. There's also, again, the potential for infrequent use and, again, permanent above-grade features. Next slide, please. So a path forward here. We can see, based on the H&H model predictions, that improving the ability of the stormwater system to carry more stormwater is predicted to significantly reduce stormwater flooding when it occurs at low tide and still have an impact even at high tide. However, stormwater flooding is still predicted to occur within the study area, no matter what we do. But you can help by implementing some of the tools on the right-hand side of your screen, like bioretention basins and permeable surfaces, and using things like rain barrels. We're able to stop stormwater runoff where it falls and not allow it to get to the stormwater system. And with that, I'm going to hand things off to my colleague, Ellen, to talk about the groundwater monitoring study.
Hey, everybody. This is a really interesting presentation so far. We did hear, as Neil said, we did hear from some of the folks in our community outreach that you were concerned with groundwater and how that might affect the flooding in the area. So as sort of an addition to this project, we were given a little bit of extra money from the Coastal Zone Management to install some monitoring wells. And so the image that you see on the right-hand side is a map of this Salem Cove neighborhood that we've been talking about. And the little light blue circles that you see are the locations of the 3 groundwater monitoring wells that were installed in late November last year. So the first one, called monitoring well number 1, or MW1, is on the corner of Connors Road, very close to East Collins. The second one, monitoring well 2, or MW2, is at the corner of Bridge Street and Lathrop Street, next to the brake and clutch facility. And then the third, monitoring well MW3, is down adjacent to the park. So we basically have sort of put them at the outer, we wanted to understand how groundwater behaves in this area. And it will help us to understand if groundwater is having an impact on the stormwater flooding that Tyler was just telling us all about. Next, and so these monitoring wells were installed, and then we put inside these wells little instruments called transducers that measure how the groundwater level goes up and down in response to storm events, in response to rainfall, in response to normal climate conditions. Next slide. We've been downloading data as we can, and this graph, I'll explain what all the lines stand for, but this graph shows us some of the initial results that we got from these groundwater monitoring wells. So towards the top of the graph, you see three colored dashed lines. The orange dashed line represents the elevation of the land surface at MW2, which is near the brake and clutch at the corner of Bridge Street and Lathrop. And the green dashed line is the land surface for MW3, which is near Collins Cove Park, and MW1 is the land surface elevation for MW1 on Connors Road. And then the other jiggly lines that you see are the actual groundwater elevations as they change over time. So MW2 is in orange. That's higher because that's a higher elevation because it's higher up and the whole area is higher in elevation. And so you can see that these data start around the beginning of December, and you see how, excuse me, groundwater moves up and down and can respond pretty quickly to some precipitation events and then goes down over time. And MW1 and MW3, given that they are so much closer to the coast and also at similar elevations, respond very similarly. One thing that we did find already is that the tides don't seem to impact the groundwater elevations or the fluctuations of the groundwater in this area. So we can see just how it responds to rainfall events and different seasons. So you'll see that the orange line ends on January 9th. That's because we've been going out about every week to download the data. And as you all are aware, we've gotten a lot of snow in January. So MW2 was covered with a big pile of snow in early January. Fortunately, MW1 and 3 we were able to still access, but then later in January, those two wells were also covered by large mounds of snow. So we anticipate that we won't be able to collect the data. We won't be able to download the data for a while, but the transducers are still collecting the data. So once the piles of snow melt and we're able to access the wells again, we'll be able to download the data, and it'll be really interesting to see. And we'll be able to see from the monitoring well data how the groundwater changes due to snow melt and rainfall event that occurs in the spring. So this will really give us much more information about how groundwater fluctuations can affect the surface flooding that you've experienced. So I'm going to hand it off now to Barbara, and she's going to talk more about community engagement.
Barbara, you're muted still.
Thank you. I just want to thank Ellen and thank everybody for coming this evening and staying with us. Community engagement is so important, and in the past we've done interviews, we've have a flood survey, and we've done meetups at Collins Cove, and we're going to continue that. So anyone here tonight who hasn't spoken with Allison or I, we'd love to, or Neil and Christian, we'd love to have a conversation with you, invite you to come. Our first meetup will be Thursday night, March 19th from 5 to 6. We usually meet in the gazebo, and hopefully it'll be a nice day and we can actually take a walk. The last couple of times we've done it, it's always been raining. But the snow will be melted by then, we hope. The other thing is that the flood survey is still up on the community engagement page for the project, and you can see the QR code, and at the end we also have the URL for that. So we want you to stay connected with us, come to a meetup, stay involved, because at this point we have these design concepts and we really need to hear from the people who use the park and who live in the neighborhood and the residents to whether this is a good what direction to go in. Next. I also wanted to take the opportunity to introduce you to a new project that the city of Salem is working on. I'm helping, and it's a MAPC project, Metropolitan Area Planning Council grant. It goes until the end of June. And this one is really looking at helping the residents. So here we were looking at municipal owned property, municipal stormwater, and what can the city do. This project is looking at what people can do in their homes. It's sort of like Mass Save, and but we're concentrating on flooding and heat. So again, there is a survey that we'd love you to take. There's a QR code there, or you can go to the Salem Public Input Engagement Hub, and there is a page on the Residential Resilience Assessment Pilot. There's a survey, and then we're doing 2 focus groups. There's a virtual focus group, and then there will be a focus group that's in person. And then those would be followed up with 4 in-home resilient assessments. So what the team is trying to do is figure out how this would work on a larger scale. So we hope you will share this information and get involved with this. Next. So next steps, community engagement is really important. The team will be refining conceptual designs, and so we need to hear from you. And there will be another public meeting, probably another virtual meeting that will be either in May or June before this project wraps up. Next. Neil?
So yeah, thanks, Barbara, and thank you, AECOM team. And I echo Barbara's thanks to everybody for attending and for sticking with us. I know we're a little bit later than we had hoped to end. A lot of materials to get through. If there are any questions, you can please enter them. We can try to answer some now, and then if we don't get to them, we can reach out with answers later. Looks like I'm looking now at the question. What about the private seawalls? How much does this matter if a private wall fails? So that's a good question. I mean, that's one of the challenges of developing these types of projects, and one of the reasons we chose the Collins Cove Park neighborhood in that particular coastal infrastructure is because we do control and own a significant portion of that coastline. But yes, if you're abutting another structure and that fails, then there is potential for the effectiveness of whatever we're doing to be impacted by that failure. So in this case, the elevation that is being proposed that Matt talked about is equal to the elevation of the abutting private wall. But yeah, if walls fail, whether they're the cities or privately owned, then that could be a problem. If there's a major flood, will some of these seawalls, berms be more damaged, need more repair, cost more to repair than others? Guessing the berm, yes, good guess. I think that's the quick answer. Is that the berm would probably be more damaged during an event and would need to be repaired more significantly. And then thank you for joining us. I think that I know this was a dense presentation. People may have a lot of questions and comments to follow up. And please reach out to the Sustainability and Resilience Department, either me or Christian team or Barbara or Allison Fry with Salem Sound Coastwatch, and we're happy to have more conversations.
And Neil, I would just say, make sure you come to one of the meetups, and they will be posted in the park, or they'll be shared with your city councilor. if you're on Facebook, or so somehow we will get the message out to people, because that's always a good way. We'll come with some diagrams, and in the past, somebody from the city has been there. I've been there, and Tyler has been able to come, and so you really have an opportunity to discuss and ask all these questions in a very warm and a friendly way when you can actually see it. So it's a good way to do it.
Definitely. Yeah. I think doing it, especially on the site, it really is it's a different type of engagement. So really helpful if people have the ability to join in person. And just, yeah, I think a big takeaway, as Tyler mentioned in his presentation, and Matt, hopefully a takeaway for you is that there are some potential measures here that we can contemplate, that can help the flooding in the area, but there is a limit to those measures, and there is a certain impact that is hard to address. Some of those larger infrastructure projects, I think, we wanted to be able to demonstrate how challenging it would be to try to address some of the flooding once you get to some of these high tide events, and major storm events in the future. So again, happy to discuss this, and please feel free to reach out with any further questions. Hope everybody has a good night. Thank you.